All right. So last time when people asked me if I'm gonna have a class on during Husferia, I assumed only one or two people will be away. But take a look at the class. So perhaps it was a good idea to not have a class during Husferia. But thank you for coming. Thank you for everyone who is over here. Today is a very important lecture. It's a very boring lecture. Last time I said it was boring, it didn't turn out to be boring, but this is actually very boring because we're going to talk about different AI models today. And when you talk about the algorithm, it becomes pretty boring. So we're going to talk about a bit of math. We're going to talk about how those algorithms work, and hopefully you'll understand it. If not, it's all right. Uh, you don't have to understand the math behind the algorithm. You don't have to learn the math behind the algorithm, but you need to know how it works when you're working with it. Everyone in Zoom, all right? Can you hear me? Okay, I'm gonna Zoom. Yeah, okay, thanks. Okay, part two of machine learning. Part two. So the last time we we went through different types of machine learning algorithms. We spoke about supervised learning, unsupervised learning, reinforcement learning, and recommender systems. Is there anything which you think which would be interesting for you to work with? Have you considered it? So the only cool thing we were able to visualize last time were these games, right? And the games were easy to work with the reinforcement learning. But with supervised learning and non-supervised learning, it's hard to visualize stuff. It's mostly like business applications and you don't really see them. Okay, so we are going to go through all of them one by one. Not all of them. The first two of them, supervised and unsupervised, we will not get time to cover reinforcement or recommender systems. We'll just go recommender systems, yes, a bit overview, half an hour overview, but not reinforcement at all. But supervised and unsupervised are very important. So let's talk about supervised learning. This image you have already seen before. And what happens in supervised machine learning is you need to carefully tell the algorithm, this is the data set which is coming to you. And when the algorithm learns, like, okay, this is data set, then the algorithm can make a prediction of what to expect and so on. So this is called training the algorithm and then validating or testing the algorithm. Now, if we were to build a supervised machine learning algorithm, these steps would be involved. So we would always start with data. Data is the base. Every algorithm, you start with the data. So you have to make sure you have the data in place. You start with data collection from the base, and then you jump onto data processing. And okay, now you have the data. You can collect data either from your watch, you can collect data from your phone, from your sensors around the house, or you can get data from social media, buy data, for example. The second step is you then go to data processing. And then this is the one which takes most amount of time because now you start with the step one, which is cleaning up the data. You look at the data and you see like, okay, there's some problem with my data. I need to take away I will take away the empty values. For example, there's some subset of information which is useful for me as a person, but not for the algorithm. Take it away. Just goes with data, clean it in a way. When the cleaning part is done, labeling. You might or might not have to label your data sets, but 90% of supervised machine learning involves data labeling in one way or the other. And data labeling is the same thing I told you last time. If you are making an algorithm which distinguishes between a person and an animal, then you have to feed the algorithm by thousands or millions of images, hundreds of thousands of images of persons and animals, and you have to label them like this is a person, this is an animal, and so on. When that labeling part is done, your job is also done. And then feature engineering, of course. I mean, feature engineering we discussed the last time. You look at your data set, and even if it's an image data set, you then start building features on your data set. And those features can be, okay, within a person and an image, person and an animal image data set, I think there's more characteristics because a person can be this tall and an animal doesn't really have to be more than this high, for example. That's one of the feature which you can define for your data set. You can also define a feature set saying like, what else is there? A tail, for example. Persons don't have a tail. Animals usually have a tail. That's also another feature you can define. So the more features you define from the data set, you kind of help out the algorithm in making a better prediction or understanding more. Now, once you are done with the feature engineering part, you then have to do the scaling part, feature scaling. Feature scaling is basically looking at all the features you have and then going through those features and then taking away the ones you think are redundant. They already are covered by some other area, or making more features. Like just doing an optimization of the features is called feature scaling. Data splitting. Now, data splitting is something we did not cover the last time. What you do is that you divide your data set. Now you're done with the data set and you will start working with the model development part. So you divide your data set into three parts. One of them is called the training part. The second is called the validation part. And the third is called the test part. Now the test part is a secret part. You don't want your model to look at this test part at all. But what you do is you start with the training part. You take like, so let's say you have like 900 and no, you have 900 images just to make it easier for everyone. You have 900 images, so you're divided into three areas, 300, 300, 300. The first 300 is the training part, the second 300 is the validation, the last 300 is the test part. And those are randomly selected pieces of data from your data set. You start with the first 300 and you give those 300 images to your data set and you train the algorithm. Once the training part is done, you now need to validate if what you have done with the model works fine, labeling works fine, data processing works fine. This is your internal test. This is an optional part. You might or might not have to do this. This is for your validation before you test the algorithm. So you kind of validate the model in a way. This is the validation part. You take the next 300 and you give it to the model and you see what kind of result the model will give you back. And then you take the feedback loop back to the machine learning model and you improve it, or back to the data and you improve it until you find that, okay, if I give it an input as a banana, I will get an output as a banana as well. And then you think it's working fine. So the two parts are complete now, the training part and the validation part. Now you're like, okay, I think I have more control over my algorithm. It works as I want it to work. You then do the testing part. Testing part is basically similar to the validation part, but in this part, you do not optimize the model. You don't fix the model because now you're testing the model with data set which the model did not see before. 300, only you have information about that. So the way people usually also do the test part is they try to get as much random data as possible in the test area. So they want to see how the model would behave in data which was never fed to the model the first time or in the validation time. You can combine the validation and the test part because validation is the optional part. It's kind of similar to the test, but validation gives you more control. So if I were to so if we were to correlate it how we do software development, so unit testing in software development, when you're making an application, building an algorithm, and you're doing unit tests on your own computer, would be the validation part. But once you deploy the algorithm and you do like testing by asking your friends or asking someone else to test your application, would be the test part. Because now the testing is done by a lot of people, not by yourself. So that's the difference between validation and test. So you can combine both, but I mean, in in um, in 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 production applications, you keep them both separate because you want to have as much impressions as possible on your data set. Okay, once you are done with the data part, we will then go to the model selection part. And I will tell you what kind of models we're gonna. So today, our focus will be this model selection only. We'll talk about different models in supervised machine learning. Which models can you use at what instance? What kind of use case will define what kind of model and so on. Once the model selection is done, you then train the model. You do validation again, testing, and then you evaluate it and deploy the model and monitor it. I think I covered a lot in the data splitting part, all of those things. Deploy the model is a production thing, so you don't have to do it and you're doing it on your computer. It's already deployed. And monitoring and maintenance is once you put it into production, you need to monitor it and see how it works. Yeah. Any questions here? So, I mean, supervised machine learning, how would non-supervised machine learning look? It's pretty much similar, except the data labeling part. So you take away the labeling part, you still have to process your data, you still have to make the data available. But feature engineering you still need to do, data cleaning you need to do. You still need to split your data set and so on. So there's a lot of things which are common to a lot of AI algorithms. Right. And as we said, we're going to focus on the models itself in today's class. We're just going to talk about models, no data, no processing, no how it works. We're going to go into the theory of model development, and we're going to talk about different use cases, and every use case will be like, okay, for this use case, we think you should use this model because this works in this way. So there are two kinds of supervised machine learning. You have one type called classification algorithms, and then there's another type called the regression algorithms. Now, these are two big types. So then within these two big types, you have further models. For example, classification can have support vector machines, decision trees, k-nearest, random forest, logistic regression, naive Bayes, and so on. There are quite a lot. Regression, you have linear regression, polynomial regression, and so forth. So for every kind of algorithm, you already have a function available in Python, and all you have to do is to call that function, and then the model will automatically run in the background. So you don't have to do much on that part. And that's the difference between normal software development and AI development, because in a normal software development, you will probably have to build the whole algorithm step by step. You'll have to optimize it. You'll have to build the data structures. You'll have to think about everything, storage and everything around it. In an AI algorithm, once you're done with data part, you just write 2 lines. It will call the model on its own, and then it will iterate and give you the prediction. So if you are working with supervised machine learning and you are working with classification problem, I mean, it will take you not the development hours, because you can switch between different models in a very quick way, but it will take you more of an analysis time, because you want to then see the output for the models coming and see, like, is this the one working for me or not? Should I switch to someone else? And you keep on switching. So what is classification and what is regression? These two types. Classification is classification. Like, we are 2 kinds of genders in this room or more, but you can classify people into those kind of classification, correct? 0, 1, the light is on or the light is off. Classify. You can classify things based on simple classification of labels. PC or Mac, for example. Yeah. The color of the chairs, for example. So you can classify different things based on different attributes. That's called classification. So you use classification when you want to predict one value or the other. And a simple example would be the gender, or it could be, it cannot be the weight, because it cannot be, it can be a weight, because if you want to predict weight by saying like a person is obese or not, that's also a classification. On the other hand, regression, what's a regression? Regression is the opposite of classification. If you do not want to predict one value or the other, and if you want to predict continuous values, that's a regression. Take the same example as weight. If you want to predict weight, but instead of predicting, okay, is a person is obese or not, you want to predict the actual weight of a person, my weight in 2 years, that would be a regression algorithm, because then you will get a value or continuous value. My weight is X. It could be X plus 1, X plus 2, X plus 3, or X minus minus, blah, 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 in a certain amount of time. That would be a regression algorithm. Let's take stock market as an example. The stock market business case can be both classification and regression at the same time, depending on what kind of problem you're trying to solve. If you're looking at the price of a stock and you want to see the price will go up or go down, now you're trying to predict high or low, right? Then you're going to use a classification algorithm. But if you're going to predict the price over the next days, then every price you're going to predict would be a specific point in time, a continuous value. That would be a regression algorithm. So even though you're working with the same data set, your output is different. And for a different kind of output, you will choose a different kind of algorithm. So I'm going to talk about different use cases you can use for classification and regression. And then we're going to jump on to two of them in classification and one of them in regression, and see like what kind of mathematics is behind it. Any questions so far? Yeah.
So where do you go when you want to go from demarcation to linear regression?
From
Like if you have classification of 10 things, you would maybe want to do regression, or do you when
Yeah.
are there like n goes towards infinite? When you want
Yeah. Oh, that's a very good question. So the question is, when would you decide that, okay, you cannot use classification, you have to go to regression? For example, if you have 10 classifications, right? That's the question. Yeah, there is a specific kind of classification called multiple classification. We're going to study that as well. I think it's over here somewhere, which actually talks about this specific thing. It will come up. It talks about specific thing that you can classify more variables than one, like true or false. You can do for 3 classification, 4-layer classification. But it's entirely up to you how you see it, because if you have so many classifications coming up, 10 classifications, then I think it's better to go for a regression algorithm, because then you're actually, no, that is a wrong answer, because classification classifies the data set on different attributes. We spoke about the color of the chairs, right? But regression would actually give you a continuous value of the data itself. So you cannot go from 10 classifications to regression, because 10 classification would be 10 different attributes of the data itself. Regression would be one classification, but the continuous value of the data.
But if you have a dice, you go from flipping a coin to flipping a dice to flipping in like 20-sided die to flipping like millions of dice. You go from classifying one thing to
Oh,
and then it becomes continuous.
that's a very challenging question. No, no, I mean, it's a very cool question. I just don't have the answer for it. Can I think about it and come back to you? I mean, it's a very interesting question. Okay. Okay. Yeah, but I'll think about it. Okay. So the use cases of classification. Can you think of any use case for classification? We've spoken about binary, non-binary. Is there any algorithm you use on a daily basis? Any application you use, which you could say like this is an example of a classification algorithm, AI built into it? We did a discussion of different AI around us in the first two classes. The email you use, email program you use, there's an automatic spam detection in it. I mean, of course, the complexity of spam is very big, but if you are looking at the spam detection algorithm, the basic role for a spam detection algorithm is to detect spam, is to see if an email is spam or not. This is a very basic function of that algorithm. And if you just focus only on that, then that is a classification algorithm. You're gonna use one of those algorithms I showed you, and you're gonna build a spam detection algorithm. This is not a regression algorithm. This is a classification because you are building a spam, if it's spam or not. Algorithm checker. When you submit your assignments, it's automatically given to this algorithm checker tool. What's the role for that tool? The role for that tool is to see if this work has been copied by someone else or not. So on that level, it's a classification algorithm. That's level one. But the level two working of that algorithm is it then tries to identify how much of the content is copied from one application, from one submission to the other one. And when you do a correlation of that one, that's a regression algorithm. That's not classification anymore. So you don't have one algorithm working over there. You have multiple algorithms working and giving information to each other. Have you seen the new chat GPT function which came out, which is more like, well, it hasn't been released yet, but it's like you can now, in addition to chatting, you can now talk with the model, you can upload pictures to the model and so on. So this is an example of multiple models which are working and providing data to each other. And it's never one AI algorithm. It's multiple AI algorithms working with each other. So you can have an environment where you build like classification, regression, supervised, non-supervised reinforcement, and you combine them all together, and then you have one big ecosystem in which these models are talking with each other and providing information. And this is also what some people are talking about, that this will actually lead to creating a general AI. And a general AI is something when you combine all those smart elements and you have different parts of the AI providing data to each other and correlating and communicating, you will then have an ecosystem where it suddenly realizes, okay, I need to do something more. And then you have an artificial being, which actually is very superior. I don't think that will happen, but that's the discussion which theologists and um, people actually talk about. Um, if you are building an e-commerce application, you want to do a classification, just saying like, okay, is the person browsing on my website, will that person buy anything, or is the person just browsing around? That's also a classification algorithm. Like I gave you the example of a person or an animal. The similar example is for a fruit. If you want to see what kind of fruit it is and you build an algorithm around it, you want to see if it's an apple or orange or something. Even if you have like tens or 20 fruits, that would still be a classification. It's not a regression. gender classification, stock market price prediction, and so on. Okay. Now, why is it clustering here? Yeah, clustering. So the opposite of classification in non-supervised machine learning. So we're talking about supervised machine learning, and supervised machine learning, there's classification. But if you look at the opposite end, and you're like, I cannot work a lot with my data. I cannot do data labeling. It's too expensive. Data is too complex, and I need to do something on. I cannot use classification at all. Then you have to look at non-supervised machine learning, and in that one, the biggest thing is called clustering. And clustering, what does clustering do? Clustering does like define over here. You take a look at a data set and you give the data set to the model, and the model tries to find patterns in the data set for you. And this is, you don't exactly know how the data set would be, and you leave it to the model to figure out patterns for the data set. And that is where it gets a bit more out of hands, because you're leaving essentially everything to the model to come back and give you a recommendation on. I'm thinking of a real world example where we would use that. Image analysis for facial recognition. In around 15 to 20 years ago, when the biggest amount of data set, ImageNet, was not released yet, we were using a lot of clustering, because it's expensive to sit down and label a data set and saying like which class or which it's not class, which ethnicity this belongs to, which area is coming from, and so on. It's a lot of work giving that much information to a data set. And we were using a lot of clustering techniques back then. And back then, our AI didn't really work that well. So if you were using a facial recognition program, or even like trying to see like the eye image or something like that, it was super hard to work with that one. Then came the data set called ImageNet. ImageNet is a collection of millions of images of human faces all around the world, labeled properly. And when that data set was available, then we saw, okay, then we don't have to use clustering anymore. We then use classification. We use that data set, we train our models, they became far superior, and then they could understand. So that led to a revolution that most of the cameras around us right now can identify a person with a much higher certainty than we had problems before. Previously, we had problems like, okay, the algorithm designed in Europe would not work for Asian people or African people or so on. And the one designed in Asia or Africa would not work on European people, because you're using different kind of data sets. But now you have so much data sets available, open source, carefully labeled, carefully processed, that you can actually use those data sets to train your models. One of the algorithms we created in Router was, have you ever used those electric scooters? Yeah. So you have multiple companies available, and the way those companies work is that once you park the scooter back, you have to take the image or picture of that scooter and send it back to the company. Because what's happened is, if you don't do that, then Oslo Commune or Beacon Commune will send a fine to that company saying like, okay, this scooter was parked in the wrong place. So the problem with taking a picture, so the problem with those companies is that when you take a picture, sometimes your friend can be standing in the background, someone can be standing in the background, you can take a picture of them. You can take a picture of sensitive information like someone's car plate information, or there can be a lot of sensitive information. And due to GDPR and data regulations, it's not allowed by those companies to look at that data. So what they started doing was, and we as well, we started using already made AI algorithms. We didn't develop anything on our own. There were tons of algorithms already made available, and we just used them, and we gave them the data sets, and it kind of blurred out all the images, it blurred out all the sensitive information, and it gave us the information like a blurred way, and we sent it back to our operator. So the reason why I'm telling you this is that face analysis has matured so much that you don't really hear so much work being done in this area anymore. And that's why you see it everywhere in every devices. And then you have people talking about privacy, that it should not be made available because you can control a certain group of population or even the whole population. Um, and you can do checks and balances on them. And it's become so cheap that you now you can even buy cameras of this small, a couple of hundred kroners, and will already have AI built into it. So people are installing them into their homes. They're putting them into their Airbnbs and illegally like looking at other people doing stuff. And that's the security and privacy concern we have. Okay. So we're not going to go into clustering to that much detail now. And we are going to just look at how classification is different from clustering. So classification is mostly assigning labels. So on and off, male or female, stock price up or down, is it going to rain or not today, and so forth. But I mean, labels can be more than one or two. If you're looking at fruits, you can have multiple labels like apple, orange, banana, so on. So then you are looking, then when you use classification to assign labels to your data set. In clustering, you do the opposite. You group data set together. You have an information about the data set, and you're like, okay, we think this data set should belong together. Put them in this space. They might not have the same label. Okay, how should I explain it? If you take the same example, and right now the clustering was done based on the color, right? Because the algorithm thought that the shape is the same. It's a potato, but the only thing different I can find is the color itself. But let's combine this data set with data set of what is similar to a potato in shape. Bread. Oh, okay, yeah, okay, bread. Yeah, small, yeah. Okay, so let's do that. If you have another data set of bread, small, and you combine that with that data set and you give it to the algorithm will still put them together. It'll cluster them because now it's clustering based on the color, and it seems that the shape is the same. It doesn't really care if it's a potato or a bread. But if we were doing classification, then it would classify them as bread and a potato, and it will also classify them as a color, as one being color, and so on. So you define the classes, but in clustering, the algorithm will cluster it. But obviously, I mean, you can control the clustering by telling it, okay, cluster it more on this or that, something like that. So clustering always happen on the properties of the data. Classification always happen on the class of the data. Yeah. Yeah. Okay. The first algorithm we're going to talk about is in classification, we're going to talk about logistic regression. This is what we discussed here. So you have quite many algorithms under classification. You have support vector machines, decision trees, k-nearest neighbor, random forest, logistic regression, and naive Bayes. So I think we will cover three of them: random forest, logistic regression, and naive Bayes, because these are the most widely used. Yeah, as we said earlier, it's also the same thing like a classification. It's just a classification, but the way logistic regression algorithm works is that if you have a data set, it will always try to make a line in your data set like an S-shaped line. So that's how you can see what's been going on in the model. You visualize the model, the data before, and you visualize the data after the model has done some predictions on it. So before, it would be more like red and blue mixed together and everything in the same place. But when you run it through a logistic regression algorithm, this is the kind of output you will receive. And the output will always be divided by an S-shaped curve. And S is the dividing line. So what the model will do is model will try to classify the data sets based on the information. In this information, you have true and false sample, or you have like blue or red color sample. And the model will work across all the data and find where it thinks there's a boundary line between the two and make like a nice S around it. Now, the if you look at the x-axis and the y-axis, it's between the value of 0 and 1. So what the model does it for simplicity, or the internal working of the model, is everything has to be mapped between a value of 0 and 1. You could have a value which would be 1 million or 10 million or so on, but then you have to transform it. And the transformation process we'll actually talk about. So the model can understand even the input, and the model will display all the output in this way. So if you want to see like, okay, what happened over here, or there's a lot of points converging. Actually, there are more points converging over there, but my hand won't go. But if you look at this point and you say like, okay, this is a interesting area, we need to investigate why are there more points on this side. And you see like a lot of points coming in from the red side are coming over here. You probably would say, okay, probably I need to tweak the model more. So the line is not here, the line goes a bit more over here. You can do that. So you can tweak the model by looking at the outputs coming from the model itself. And it could be the other way around as well. You can tweak the model going up or down and move left to right by a simple cost function. We'll talk about that cost function. I do feel like I'm losing the crowd. It's becoming a bit theoretical. But let's take a break now. And we come back in 9:25. Yeah, 9:25. So today I was coming to the class, and my son was asking like where I was going, and I was like, I'm gonna go and teach a class, and he doesn't understand the concept. So I tried to explain him like he goes to Barnehage, and I'm like, you have some teachers over there, and then I'm going to teach my students. And then he said you can't go to the class without a book. So he gave me a book, and he told me that I have to teach this book. I'm like, okay. So I promised him I'll show this to you. So I have. Okay. Logistic regression. So as mentioned earlier, when you start giving data to your logistic regression algorithm, you then expect the algorithm to give some sort of output between 0 and 1. So let's dig into how this S thing works, how this model works, what's the math behind it, how does it take all the input values and map them between 0 and 1. So there is a function called the sigmoid function, and the sigmoid function, it's very important in logistic regression. What logistic regression does it uses a threshold value. And the threshold value is, since everything is between 0 and 1, that's what logistic regression understands. It will try to map everything between 0 and 1. And the threshold value is something you specify. Okay, you can say like, so threshold value 0.5 means there's a 50% chance of something between being one or the other. If you put the threshold value as 0.4, then you have a 40 and a 60% chance of something happening one or the other. 0.3 is 70-30, 0.2, and so on, and then all of that. So every time you change the value, the threshold value, the line goes up and down, and so does the prediction for the model too. Over here, the prediction is 0.5. The threshold value is 0.5 because you can clearly see it's 50% divided on one side or the other. Now, remember I told you about this problem. This could be a problem for some, this could not be a problem. But if it's a problem for you and you want more division between two data sets, you could increase or decrease the threshold value, and the threshold value will go up or down. Now, I spoke about 0.2, 0.3, 0.4, but you can also do 0.5555555, and so on. You can do it with that minute detail as well. Yeah, it's the algorithm logistic regression. We use it to predict the occurrence of some event, any kind of event. So if you're trying to, if you're making if you're trying to predict if it will rain or not, logistic regression is the go-to algorithm for those kind of use cases. Spam detection, if you want to see, if you're working in health, you want to see people have diabetes or not, logistic regression. Cancer detection, but obviously those algorithms have a lot more going on in the backend because you have image analysis, you have, yeah. So, but logistic is one of them you'll be using. Now, within logistic regression, there are various types of logistic regression. You have a simple type, which would be the binary type we spoke about, very simple, pass or fail, true or false, and so on. But you also have a multiple class logistic regression. And that could be within animals, it could be a cat, a dog, or a sheep, or within fruits, it can be apple, oranges, banana, and so forth. Multiple classes of logistic regression. And then you have different kind of ordinals. It can be on a lower scale or a medium scale or a high scale, and so on. Let's try to design a logistic regression algorithm. So what we will do is I'm going to show you an example, and we're going to go through different parts of the code, and we're going to see how that model works. And what we will cover are two parts. We will cover the development of the model and the evaluation of the algorithm itself. Now, within your Python application, within your coding application, these are just 2 or 3 lines. But you need to understand what those 2 or 3 lines do. So the data set you have is the data set of how many hours students have been sleeping and how many hours they have been using for their education. And using that data set, you now need to predict if a person will fail or pass the exam. That data set alone. It's a very stupid kind of data set, but okay, let's start with that. You only have these 2 information, and then you need to have, and using that, only these 2 information, you now need to make logistic regression algorithm to predict a person will pass or fail. And the pass and fail is a very easy thing, right? Pass is 1, fail is 0. So that's how, so this is very important. When you look at your use case, you need to understand what do you want the algorithm to do. Here, I asked you if the person would pass or fail. Now you have to visualize what kind of question am I asking you. And if I ask you, make an algorithm which tells me if a person will pass or fail, that use case itself says it's a logistic regression use case because your output will be 0 or 1, binary 0 or 1. But if I were to say, like, okay, tell me how many hours this person will sleep, that's not a classification problem anymore. That's a regression problem because now you're giving me a continuous information. You're giving me number of hours a person will sleep. That's the difference between the two use cases. Same data set, different kind of use cases. So for pass or fail, that's the output I need. You will first visualize the data set, and data set is all over the place. You in this image you have 4 inputs, right? But when you visualize, so actually you have more data sets over here. So you did a simple plotting on using Python application, again, simple 1 line of code. And you see like data is all over the place. You have information about hours slept, you have hours studied, and you also have information on what happened to those students historically. So you took information so I took information on you, for example. I took information on the last 2 years, and I was like, okay, you studied this much for this exam, and then you slept this much, and then you passed or you failed, and so on. And I gave you the data set, and then number of hours slept and studied, and you plotted it over there. Now, what you do is, this part is data analysis. This is the data preparation. This is looking at data and trying to figure out, okay, what has been done. Data labeling part was over there. We looked at the number of hours studied and slept, and we labeled it as pass or fail, pass or fail. This is the labeling part. And when the visualization is done, you then move on to the model selection. You chose the logistic regression model, and now you're going to do now you're going to try to map all the values between 0 and 1 right now. So right now everything is already between 0 and 1, but sometimes the value is not between 0 and 1. Then you have to use this function, which is a sigmoid activation. What it does is it transforms whatever value you have, and it transforms them between 0 and 1 so the model can understand. This is an important thing because you cannot use data as is. You have to transform the data to a format which the model can understand. In logistic regression, the model only understands values between 0 and 1. So when you have to do the transformation, you have to use this sigmoid function. This is the mathematical formula of the sigmoid function. We will not go into details of how it works, but you don't have to implement it. Again, this is also 1 line of Python code, and it will do this automatically for you. Once the values are transformed, you then define a threshold value. Now, the threshold value is entirely up to you. This is, you identify the threshold value by doing multiple steps and by looking at what the output comes out. By default, we start with a 50-50 approach. We always go for a 50-50 approach because that's the easiest thing to go forward. And it's a classification problem, right? You're trying to get like a true or false, 1 or 2, 1 or 2. So you start with the 0.5 thing. And the threshold value would be, if a threshold value is 0.5, you can say, okay, if the output for the prediction is less than 0.5, that means it's a fail. If output of prediction is greater than 0.5, then the person has actually passed. And internally in the model, this is how it will work. It will make like a threshold value, and you'll see like everything above is a pass and down is a fail. So now, since we have used the sigmoid function to transform the data between 0 and 1, and we have made a decision boundary, like we have put a threshold value, 0.5, we can now write our prediction function. And the prediction function just looks at the input of the data, threshold value, and does a prediction for you based on what kind of input you will provide. Now, the model will probably give you, if it gives you 0.4 and you had a threshold value as 0.5, then you know it's a fail. If the model gives you 0.5, it's a pass, and everything above is a pass. And once you are done with the prediction, you kind of evaluate. Now, the evaluation part is also where the model helps you evaluate itself. There's a process called cost function. Okay, what is a cost function? Let's see. Over here, you make the model, but this is a very good picture. Everything is fine. Everything looks good. But let's say this line was over here, and you're like, it's not giving me the right prediction, and the model is not working well. And you're like, okay, I can tweak it more. You change the threshold value, you move it there, but when you move the threshold value, it keeps on giving you more error. Like, okay, it fixes it over here, but it still has a problem over here. There's so much problem with the data set, something you didn't do, something the model didn't work fine, that you cannot just fix it by moving the data set, moving threshold value, or fixing a data set. You need the model to optimize on its own. That is called a cost function. What a cost function does it, the model looks at the problems and tries to reduce the errors on its own. And there are multiple runs of that cost function. I'll show you. Last line. A cost function is a measure of how wrong the model is in the terms of its ability, between X and Y. Cost function calculates and gives you a value saying, like, this is an evaluation of the model itself. I am wrong by this extent, and I need to fix myself. So what we do then is we use different kind of cost functions which identify how wrong the model is, and those functions fix the model on its own. So one of the cost functions, there are multiple kind of cost functions. One of those cost functions is called gradient descent. And what that algorithm does, it kind of runs over and over again until it finds a way to fix the model on its own. So, so let's say you saw some kind of problem, and you saw like the model gave a prediction which was so off. That was a starting point, and you actually needed the final value, which was close somewhere over here. So you then ran gradient descent cost function on the model itself. Again, one single line of code, and it will start executing it. When you run the starting point, it will do multiple iterations, and it will automatically find a point where it will say, like, now I have converged to a point where I don't think I can. There will still be errors. You will never get 100% accurate model, but over here it will do so many iterations that it will say, like, okay, this is where I think is the most optimal point, and I should stop, and it will stop over there. And that will be your result of the model, which will be acceptable model for you, which the model does not have to fix its own self. If I were to visualize it in a diagram, this is how, in animation, this is how it will work. So you start with an initial version of the model. It's very off, but every time it runs, it tries to find, it does an iteration. It can be all over the place, but it will try to find a value and we'll try to converge on that value. And we'll say like, okay, I've tried this conversion, this iteration so many times that I cannot find a more optimal path or a more optimal prediction. And then it will stop. In right now in this animation, this is doing few iterations, but in reality, this can be all over the place. This can go like this, go all the way over here, and does more iteration and does all everything like this until it tries to stabilize over here. And that would be the best output for you. So I'm going to repeat myself. You do three kind of things. You start with the sigmoid function. The sigmoid function maps the values from different kind of values to 0 and 1. You then define a threshold value. You tell the model, I think the prediction should be between equally divided 50-50 or yeah, start with 50-50. That's the most standard one. Once you are done with that, you have to use the cost function. The cost function is a self-optimization thing by the model to achieve the right values for you. And then you get the prediction. So this is a very simple Python code. What we have done is like, if the probability is greater than 0.5, return 1. If it's less than 0, it's like, yeah, it's very simple. And you always get probabilities in terms of numbers like this. 0.96, 0.44. If you multiply that with 100, if you want to see this as a percentage, it will be 96%, 44%, okay, 1% something, 78%, 97, and yeah, 0.4%. Yeah, and then if we were to finalize the logistic regression, you would train the model. Now you're done with the development part. You're done with the evaluation part. No, you're done with the development part. You do the training of the model, evaluate the model, which we have done, and you see the accuracy of the outputs by doing the test set. The test set which we spoke initially, you check the accuracy. You see how much prediction is coming out, and then you're done. And that's how you create an AI model. How was it? It's a very different way of working from our normal software development. We get simple instructions and we write lines of code, and it's easier to work in normal software development because you don't have to go back and forth. You fix the bugs. In AI, you fix the bugs, you fix the code, you fix the bugs. No, bugs are not the same in AI. In AI, you fix the data and you fix and you tweak the model to work around the data. So it's a different way of looking at software. It's not how we have been used to working with software development, object-oriented programming, structured programming. You stop thinking about everything over there. We stop thinking about arrays or structures or memory issues or something like that. We start thinking of a different kind of world altogether. You start looking at problems and you try to identify solutions to those problems because you're looking at data. You have to be able to look at graphs if you want to work with machine learning, because you have to visualize what happened before AI, before I used the model. How was the data then? And what happened with the data afterwards, after the model did its prediction, and so on and so on. So when we hire AI programmers, we are looking for people who can do data analysis. You need to know what kind of data you have. We are looking for data engineers. You need to do data processing. You need to do data labeling. You need to combine your data set with other data set. You need to collect data. So data pipelines, you have to make those data pipelines. But how would you make those data pipelines if you're not a software programmer? So you need to be a software programmer. You need to know how development works, which is a very good foundation. All of you are programmers. And then when you are done with software, with data engineering, then you need to focus on the machine learning part. And then forget about the data, focus on the machine learning. You need to optimize the model, tweak the model so it gives you the right value. And even by doing that, you will realize you did the wrong step. You chose the wrong model to start with. You probably should not even be working with logistic regression. So you scrap the whole thing and you start working with another model called naive Bayes, for example, and you start working with that one. You realize you did something wrong over there. You jump to the third one and fourth one and fifth one. That's where you spend most of the time in AI, on the model part, on the data part, and so on. So you do not optimize your algorithm the same way you would be optimizing in a Java algorithm or a .NET application. It's a different kind of world altogether. And then we have LLMs, which is a different kind of working on its own. It's not software development, it's prompt engineering and prompting how to get maximum value from your chatbot, for example. Any questions before I move on to the second algorithm? No? Go through the slides again. I mean, it's you will learn more. And this was the most thorough explanation of a classification algorithm, logistic regression. The second one, we might not go into that details, but it gives you an idea generally how an AI model works. Okay, the second kind of classification algorithm we have is a naive Bayes classification algorithm. Hmm. So this is a classification, but it's a bit more complicated than giving you a true or false, one type or the other. When you have a data set which is a bit more complicated, and you say like, okay, instead of just putting information about a student sleeping and how much hours a person spent on studying the exam, if you have more information in the data set, which is a bit more complicated, then probably we need to use naive Bayes. For example, a fruit has more characteristics. A fruit is, if you're looking at three kind of fruits, we are looking at an orange, apple, and okay, if you're looking at those two, and the characteristic you will see, they're round, they have a certain shape, they cannot be super big, they come into a specific size, and so on. And yeah, but something else can be red, round, and about 3 inches in diameter, and it could not be a fruit itself. It could be a golf ball, for example, or it could be a tennis ball, for example, and so on. So if you have these kind of things, happening, then you probably have to assume you have more features coming in, and you don't want the features to be correlated with each other. Then you will be using a naive Bayes algorithm. Now, the problem with the naive Bayes algorithm is that if you run that algorithm, it will, and if you give them a data set of, if you give it a data set of, you train it with data set of apples and oranges and everything which is round in the fruit category, and if you test it in real world, and if you give it a data set of, if you give it an image of a tennis ball, for example, it will also tell you that this is an orange or this is a fruit. That's the problem. I wanted to show you one image, which is a pretty cool image. Tomato, thank you. Yeah. Let's see. Okay, before I show you that image, this is the formula which this algorithm uses. So like others, it also learns on from its history, and what it tries to see, that it tries to find the probability of A happening, provided that B has happened before. What does that mean? That means like, for in simple terms, it's like, okay, I want to see if this image is a fruit or not. But the only way it can figure out if it's a fruit or not is by looking at the data set I provided to train it. So it will look at that. Yeah. It's a very simple thing. Yeah. Discrete mathematics. We will not go into understanding how the mathematical formula works, but you need to know the difference between the math in naive Bayes. This is the formula for that algorithm, and the algorithm which is logistic regression. Where are you? Okay, I can't find it. It's here, here. Logistic regression is this. This is the prediction we use for logistic regression. If you give me two minutes, I'm going to exit the slide and bring up the second image I actually want to show you. Just give me 1 second. Somehow the Zoom people cannot see my screen. Can everyone on Zoom see my screen or no? Okay, wait. That's why. Okay, probably now you can see it. Okay, good. So this is so so let's assume that you're building a naive Bayes algorithm and you want to train it using ping pong balls. And you use a lot of ping pong balls, and now you're testing the algorithm. You tested it using something similar to ping pong, which were eggs, and the algorithm gave you 100% confidence, saying like, this is a ping pong ball. It's not a ping pong ball, but in a naive Bayes algorithm, this looks similar to a ping pong ball. And it was like, okay, since I've been trained on ping pong ball, I think this is also a ball. On the other hand, if you were training the algorithm on images of a dog, a specific breed of dog, the algorithm has now here the algorithm has only been trained on dog images, dog faces only, this specific breed of dog. And this is not classification, this is naive Bayes. A naive Bayes algorithm says like, if the same features exist in other kind of images, then this is also a dog. And that's where the prediction is completely wrong. Because over here, you've given it some kind of food images and it says like, this is also a dog. Now, this is probably what you hear in the media too, that the algorithm was so off and it did something super wrong and so forth. And probably this is also one of the algorithms being used in when you get this problem like, oh, um, the algorithm is racist towards certain kind of people because it's not able to see their skin color or something while designing an image recognition algorithm. This is the problem because if you are using a naive Bayes algorithm, it's trained on specific traits of people, and it assumes that this is also the same one, and it gives you a wrong kind of prediction. This problem which happened that I don't know if you heard about it, but they were looking at, and yeah, so these kind of algorithms can have, so intentionally no one would want to make a racist or that kind of algorithm, but the algorithm itself is designed in a way that it can give you that kind of output. And the person designing would never want to say like, okay, I'm only going to use this kind of data set or that data set. No, they want to use as much data as possible. But sometimes it becomes an ethical problem that now we're looking at a funny example. But if you take the same example and you put it into certain people and you're making a crime prediction algorithm, it only predicts certain color of people and not the other color of people. The people who are designing the algorithm never think about making a racist algorithm. They actually work with the data set they have and they work with the algorithms they have. Now, it's very hard to build a naive Bayes algorithm from scratch because it works on a specific mathematical formula behind it. So you have to rely on the statistical programming of the model, the calculation behind it. The only thing you can do to tweak it to have more data set, have more variety available. The algorithm will do what it's supposed to do. It will try to find patterns. And when the patterns are funny in this way, it's fun. We can laugh about it. But in real world, if it starts giving you a prediction of a person who you will always have to, the police or security service always have to stop, that's wrong. So then you have to, the only way you can fix this is by giving it a larger side of data set and telling it, okay, don't look at that data set because this is not right. So over here, this problem can be solved. This dog problem can be solved by giving it more amount of data and telling like, okay, this is actually a food image. Classify this as a food and classify this as a dog and so on. Okay, any questions here? We will study naive Bayes algorithm in part 3 of our lecture. Yeah. So I think it's better if we finish up our lecture today. And yeah, that would be in the next class. Any questions so far on this? No? Perfect. You all learned very well. Then let's meet again in the next class. One of the assignments, the last assignment, is a data labeling assignment. We have decided to replace this with the prompt engineering assignment. But for you to be able to do a prompt engineering, there will be a lecture on prompt engineering, what it is, how to work with prompt engineering. That's in the LLM scales area. So I'm going very fast into covering and finishing up machine learning. 2 more lectures on machine learning. Then we'll talk about ethical side of AI. Then we will focus on the LLM part. And I think you should know about LLM because this is what everyone is talking about now. So 2 lectures on LLM, 3 more lectures on the remaining AI. So 5 lectures, and then we are done with the class. Then we'll have, if we have some time, we can cover like the bonus sides of AI. Thank you so much.